Okay, hello, welcome. In this short video for my 430 operating systems class, I want to talk a little bit about your assignment for specifically, but in general, hopefully just give a little bit of a short talk about the software, the operating system software side of memory management, and specifically, I want to talk about page replacement schemes. But before I do that, and I want to talk about page replacement schemes and especially talk about the ones that you're supposed to be doing for your assignment 4, but I want to talk about the other ones as well that our textbook discusses. And I want to talk, just give a few thoughts about memory management in particular. So this is our from Chapter 8 of our textbook, the beginning of the section 2 in Chapter 8, talking about the software side of the different policies, the different algorithms needed to manage memory and needed to implement virtual memory. Okay, so your assignment 4, and I'm mostly going to be talking today about the replacement policy part, the algorithms here for deciding if when memory becomes full, which page is going to be selected to be replaced. Okay. So, but do keep in mind that there are, all these other things. So before memory becomes full, there is a fundamental question about where do you place new pages in memory. So, and these are known as the placement policies. So for a paging system, the placement policy is trivial. I mean, if there is some free memory, if there's a free frame of memory. Any free frame is as good as another free frame, so you can just pick the next free frame and place your new page into that free frame. So placement policies are more important if you have a segmentation system rather than a paging system, right? So if you have a segmentation system, it's important, whether you're going to pick a free block of memory that's the best fit, or just the first one you can find that fits, so those types of things that we talked about previously, or that you should have read about previously in the context of memory management for operating systems. Another thing I just want to briefly kind of mention, the resident set management, make certain you read and understand it. I mean, this is important too. So this has to do with your policy. So if you're implementing a multi-programming system, you've got multiple processes running at any given time in your system. So when you need to make a page replacement decision, you can have several different policies. So, for example, you could have that a process that's running gets a certain number, a fixed number of physical frames of memory. So with that fixed resident size policy, the process, if the process is currently using all of its allocated frames of memory, you have to select one of the frames. If you need to load a new page for a process, you need to select just one of the frames that process owns to be replaced by a new one, right? So that's what fixed is. And variable is as it sounds. So if you have processes and you're allowing variable resident sizes, in that case, the number of frames that a process has could change, could grow and shrink. So in that case, when you need to replace, when memory becomes full, you might remove a page from a physical frame from another process, from a different process, to load in a page from a new process. So in that case, the resident set size of one process shrinks while the other one grows. Okay. These are related to the replacement scope. So global is the idea that global is related to, is going to be used usually for a variable resident set size, right? So if you make a global replacement decision, that means any physical frame in memory could be selected to be the one that's replaced. if you need to bring in a new page, irregardless of which process owns that page. So global replacement scope naturally goes with a variable resident set size for your processes. Likewise, local is more often associated with a fixed resident size. So if you have a local replacement scope, the usual idea of a local scope is that you only consider the pages for the particular process that you need to replace a page for as the set that you're going to select a replacement from. Okay, so that's basically it. Make sure you understand these policies and the others as well, cleaning policies and fetch policies and things. But we're mostly going to talk about replacement policies now. And especially, I want to go through the four basic algorithms that our textbook talks about. The optimal page replacement policy, and then least recently used first in, first out, and clock policies, okay? So, our textbook gives some examples of running those policies. I'm going to give an example with a different set of page streams here. So, on the whiteboard here, I've already got, for all these examples, I'm going to use the same page stream. So make certain that you understand this page stream here. So, in this case, what this represents is time is going from left to right for the page streams here. So, at time 1, there's a reference to page 6. So again, I usually, when I see these simulations from our textbook, I usually just think of this, that we're using a global page replacement, we're using a global resident set policy, okay? So I don't worry about which process owns which page here. So just think of, we possibly have multiple processes, but we have some reference to page 6 of a process. So that happens at time 1. And then at time 2, we have a reference to a different page. So we need to access memory. We need to access like a variable on page 5 at time step 2. So maybe we need to read a value on page 5 or write it. So that's what's happening with these page streams. So at time 3, we've got a reference to some variable on page 2, and so on. So in this case, I've got 12 different time steps, and at each time step there's a reference to a different page. These are virtual page numbers, so there's a reference to a different virtual page number of memory. So initially, in this simulation, we're going to be illustrating a system that has 4 physical pages of memory. So it's 4 physical frames of memory. Our textbook calls a page that's physically in memory as a frame of memory. Okay. So we have 4 frames, stream 1, 2, 3, and 4, okay? So initially, when memory is empty, so at time 1, no pages have been loaded to physical frames of memory, okay? So this represents the state of memory at time 1 here, and we have nothing loaded yet. So let's first do the optimal page replacement policy, okay? So optimal can't be implemented on a real operating system, because in order to implement the optimal page replacement policy, you have to be able to see into the future. So you can prove that you can get optimal page replacement by looking into the future. So whenever I have a page and I need to replace a frame in memory with a new page that's being referenced, you can show that it's optimal to find the page that's going to be referenced furthest in the future and to select that one for replacement, okay? So here, optimal is in the sense of, for all of these page replacement policies, what we want to do is we want to minimize the number of page replacements that we have to do. So we want to maximize the number of what are known as hits, page reference hits, and we want to minimize the number of misses, the number of page faults that occur that require us to make a replacement decision and select a page to be removed so we can bring in a new page, okay, so we can load a new page. So that's the whole thing. So for all these policies, we're comparing to how well they do to minimize page faults and to maximize the page hit ratio, okay? So let's just do it. So optimal, so another thing, for all of these page replacement different algorithms, The initial, when memory is empty, we're not really making a page replacement decision yet. So page replacement doesn't happen until memory is full, and I have to select a page to kick out of memory to replace with a new page. Okay, so really, until memory becomes full, you're actually making a placement decision, not a replacement decision, right? So usually, if we're doing a paging system, so initially, if we have free frames of memory, we just keep a pointer to the next free frame in memory, and we just select the next free frame. Okay, so initially, memory is empty, so we might be pointing to frame 1. So when we have a reference to 6, we need to place frame 6 in memory. So we're going to place it in frame 1 here. So now for the next. So for the next time in memory, we have a reference to page 5. Page 5 is not in memory, so we need to load it. But we have some free space available in memory, so we're just going to place it at the next free space. So page 5 will go into frame 2, and then so on. So when we have a reference to page 2, we currently have frames 1 and 2 have pages in them, and frame 2 will be placed in memory at frame 3. Then finally we have a reference to 4. Okay, so now at this point, memory has become full. Now, the next time we have a reference to a page that's not in memory, we're going to have to make a replacement decision. So if the page isn't in memory, in order for that process to continue working, that page has to be loaded from secondary storage into physical memory, into a physical frame of memory, and then once it's loaded, the process can access the variable on that page of memory and continue processing. Right. So we're only going to be talking about hits or misses from this point forward. So from these 8 page references, and we'll be calculating our page hit and our page fault ratio, our page miss ratios, just from these 8 memory references after memory became full. Okay, so here the very first what happened. So for all these page replacement algorithms, the first thing you always ask is, so I have a reference to some variable on page 2. Is this a hit or a miss? Okay. In this case, page 2 is already in memory. It's in physical frame 3. So this is actually a hit. So when a hit occurs, we don't have to do a replacement. So when there's a page hit, the variable that the process is accessing on page 2 is already in physical memory, so it can just read or write that variable and continue processing. Right? Likewise, for the next reference, we have another hit. So we have 2 page hits in a row, 6, 5. And notice that memory stays the same now. So we still have the same contents of memory whenever a page hit occurs. So now, at this time step, when we have a reference to some variable on page 3, this is our first example of a page fault, because 3 is not currently in memory. And now, since memory is full, we're going to have to make our first page replacement decision, okay? And here, we're using the optimal algorithm to make our page replacement decision, okay? So again, to emphasize this, optimal can't be implemented on real operating systems. You can only implement an optimal policy in a simulation. So in theory, so what we have to do is we have to be able to look into the future to implement the optimal page replacement algorithm. Okay, and on a real operating system, you can't predict the future. The references to pages are going to be random. You can't know when a reference to a page is going to occur until you actually run the processes. Okay, so but here, if we're doing a simulation, we can look into the future. So we know that we've got pages 6, 5, 2, and 4 in memory. So we have to figure out which one is going to be referenced the furthest in the future. Okay. So 5 is going to be referenced the least for the closest in the future. So we definitely don't want to replace page 5. Then 6 comes next. Okay. So you'll notice, though, that 2 and 4, I mean, if my simulation continued on, maybe they would be referenced further in the future, but we don't see any reference in the future to page 2 or 4. So in that case, it's ambiguous which page the optimal replacement should replace. But in this case, either one, 2 or 4, is fine to select, because we don't know. Maybe the operating system stops at this point, or maybe it just continues on, but we don't have that information for our simulation. So you can select either 2 or 4 in that case if the information is ambiguous, if you don't know for sure. I usually just select the one in a round robin style. So in this case, page 2 was loaded before page 4, so we'll select page 2 to be replaced. Okay, so page 2 will get kicked out and replaced by page 3 at this step of memory. All the other pages stay the same. So 6, 5, and 4 are in frames 1, 2, and 4. And page 3 is now in frame 3. Okay, so that's the optimal replacement, and we can continue on. So now we have a reference to 5. That's another hit. Memory doesn't change whenever you have a hit. 6, 5, 3, 4. We have another hit, a reference to page 3. Another hit, a reference to page 6. And then we have our second miss, so our second page fault occurs. So here, again, the term page fault comes from virtual memory management system. So the process that was running had a reference to a variable on page 7. Page 7 is on secondary storage, it's not in main memory, so there's a page fault. That process has to be blocked until we load that page into physical memory, and then we can restart the process. So now, again, we're going to have to select a page for replacement. Using again, it's ambiguous. Only page 5 do we see as reference. So page 6, 5, 3, page 6, 3, and 4 could potentially be replaced here. By what I said before, 6 was the earliest between 6, 3, and 4, so I'll go ahead and replace page 6 here. So now I'll have page 7, 5, 3, 4. But it would have been valid to replace page 3 or page 4 here, since we don't have information. So that was a page fault. And then our last reference here, we have a page hit, okay? So this is our final contents of memory. Given for my 2 page replacements, I had to make a bit of an arbitrary decision, because I had more than one page that could be a candidate for replacement according to the optimal policy. But given the 2 decisions I made, replacing page 2 here and replacing page 6 here, I end up with this contents of memory. All right. So now, among these 1, 2, 3, 4, 5, 6, 7, 8, among these 8 page references where I had to make a replacement decision, I can calculate for example, the page fault ratio. So I had 2 faults out of 8. So my fault ratio is 2 out of 8, or 1/4. Okay. And likewise, you could also be asked to calculate the hit ratio for a page replacement algorithm. The hit ratio and false ratio, page fault ratio, should always be complements of each other. So in this case, the complement for my page hit ratio would be 6 hits out of 8, because I should have had 6, 1, 2, 3, 4, 5, 6 page hits out of the 8 references. All right. So that's just our page fault or page hit ratio whenever you're calculating those for one of these page replacement schemes. All right. So optimal cannot be implemented in a real operating system. So we need algorithms that you can actually implement. So the simplest algorithm that you can actually implement is known as the Fifo, the first in, first out page replacement algorithm. So in Fifo, we're going to treat our physical memory just as a circular buffer, okay? So kind of like we did treating the free frames as a buffer initially. We're going to do that for all of the page replacement decisions that we need to make when we do Fifo. So again, we're going to start out, all of these algorithms will start out the same way, because until memory becomes full, we're really just doing page replacement, okay? And we're just going to be treating the buffer as a treating the physical frames of memory as a circular buffer until memory becomes full, and then we start needing to perform a page replacement algorithm. So I won't even say these. So basically, memory just gets filled up. And now at this point, we have our memory is full, so we may have to be making page replacement decisions from this point forward. But our first two references as well are always going to be hits if we're using the same stream of page references. So nothing's going to happen for my reference to 2 because that's a hit. Page 2 was already in memory, and also page 4 is already in memory, so that's a hit. So now for page 3, that's going to be our first page fault, where we're going to illustrate this for the first in, first out algorithm. So now I need to remember, I need to keep track of my some pointer into memory that's going to be used in order to treat the frames as a circular buffer here. So normally we would think that the pointer starts at the first frame of memory after memory becomes full, okay? So my pointer is pointing here to frame 1, so Fifo just says wherever my pointer is pointing, select that page for replacement, and then move the pointer to the next frame for the next time when we have a page fault and need to make a replacement decision. So 6 will get kicked out and replaced with 3. My pointer will be moved to frame 2, to the next physical frame of memory, and the rest of the frames here still have the contents they had before, 524. So now memory has the pages 3, 5, 2, 4 in it. So now we have a reference to 5, so that's a hit because 5 is here in frame 2. So memory doesn't change, and the frame pointer is still going to be pointing to frame 2 here, so that doesn't change either. And then we have another hit, so a reference to page 3. And my frame pointer is still pointing to frame 2 here. Now we have another page fault, a reference to page 6. Page 6 is not in memory. The contents of memory, in case you can't see it too well, are 3, 5, 2, and 4 in our 4 frames now. So I'm going to, the frame pointer is pointing to frame 2, so I'm going to kick out page 5 and replace it with page 6. So our contents are now 3, 6, 2, 4, all right? Now we have another page fault. We have a reference to page 7. And our frame pointer is pointing here to frame 3 now, so it got moved from frame 2 to frame 3. So we're going to kick out our 2 and replace it with 7. So our contents are now 3, 6, 7, 4. And then 5 causes another page fault. So unfortunately we kicked out 5 back here at this time step, and we just need to reload it again. So now we're going to our frame pointer after we loaded 7 got advanced to frame 4. So now we're going to replace page 4 in frame 4 with page 5. All right, and so on. So this is the final contents of our physical memory after doing Fifo page replacement. So notice it is different, what you would expect. These are different policies, so they'll make different decisions of which page to select for replacement, given the policy. Here for Fifo, we had a page fault ratio. We had 4 faults out of our 8 references when we had to make replacement decisions, or possibly had to make replacement decisions. So we have a fault ratio of 4 out of 8, and the complement, means that our hit ratio was also 4 out of 8. All right. In general, Fifo is the worst algorithm in terms of performance, in terms of minimizing the page faults. Okay, so since Fifo first in, first out doesn't take into account at all the likelihood that a page is going to be needed again, it's very likely using just just treating the buffer as a circular buffer, just treating memory as a circular buffer, then you're going to end up picking pages that to move out of memory that just need to be referenced and moved back into memory quick. They're just going to be needed real quickly again. So they get kicked out, but then you just have to turn right around and load them back into memory again. So Fifo often has bad performance. You get lots of unnecessary page faults because of that. All right. So LRU is an attempt to create an algorithm that performs well. So LRU is going to try to take into account how likely it is that a page is going to be needed, and not select pages that are likely to be needed for replacement. Select pages that don't seem to be needed anymore. Okay, but again, we can't look into the future to implement the optimal page we should select. But if we look into the past, and if we look into our history instead of looking into the future, pages that have been being used a lot recently are likely to still be needed, and are still going to be needed, are have a good probability to still be needed again in the near future. Okay, so the argument goes, in least recently used, if we look back into our history, the page that's been used the furthest back in history, so the one that was least recently used, is likely, maybe it's not being used anymore. So maybe the variables on that page have gone out of scope, or we're done processing the variables on that page. So those are good candidates to be kicked out. All right. So that's what LRU is. So in practical terms, it means that we have to look back in history, find the page that was used furthest back in history, and select that for replacement. All right. So we're going to start out again like we did before. Just we have to do page placements instead of replacements. So we're going to end up. I won't even show them. So we're going to end up with memory with the content 6524 after our first four-page references here in memory. And then we're going to have a hit again as usual. So a reference to page 2. It's already in memory. And then we have another hit. And now we have a page fault. A reference to 3 is not in memory. So now we need to look back in history to find the page that was least recently used. Okay. So among these, 4 was the most recently used. So it was just referenced, followed by 2. So we shouldn't select 4 or 2. 4242. And then 5. 5 comes in third. And then the one that was least recently used, the one that was used furthest back in history, is page 6. Okay. So here we end up making the same decision that we would do for Fifo, but that's just a coincidence. So we were making this decision based on the page that was least recently used. So 6 is kicked out and replaced with 3. And then we continue on. So we have a reference to page 5. That's a hit. Memory doesn't change for a hit. We have a reference to page 3. That's a hit. We have a reference to page 6. That's a fault. So now we have to go back through our history again. 3 was most recently used, followed by 5, followed by 4. So if we go back, 6 has not been referenced since all the way back to our very first page reference. So we will kick page 6 out. I'm sorry, we have a reference to 6, so 5 and 3, followed by 4, so 2, among the pages in memory, sorry for the confusion here, so the pages in memory are 3, 5, 2, 4, those are the ones we have to select among. So in order from most to least recently used, 3 was most recently, followed by 5, followed by 4, and then 2 was least recently used. So we're going to select 2 to be kicked out. And we will replace it with page 6. All right, so our contents are now 3, 5, 6, 4. We're going to have another page fault, reference to 7. 7 is not in memory. So 3 was most recently used, followed by 5, followed by 4. I skipped 6. So 6 was most recently used. So we just referenced 6. So 6 followed by 3, next followed by 5, leaving 4 as the least recently used. Okay, so we'll kick out 4, replace it with 7. There we go. And then finally we end up with a page with a hit. So a reference to 5, which is already in memory. Alright, so in this case, let's calculate our page fault ratio. We had 3 faults out of 8, so a bit better than least recently used. Or the complement, the hit ratio was 5 out of 8. Okay? So for all of these, you want to be maximizing your hits or trying to minimize your page faults. That determines which replacement algorithms are better and which are worse. Okay? So the LRU can't do quite as good as optimal, but it can get pretty close. But unfortunately, there's a lot of overhead. So to completely implement LRU, so one way you can do that, and for your programming assignment 4, you're supposed to be implementing both Fifo and LRU. So one way you can implement LRU is you could just keep a timestamp, okay? So every time a page is referenced, you could just keep a timestamp of when that page was referenced. So here, we could think of just using time, like this was timestamp 1, this was timestamp 2, this was timestamp 3, 4, 5, 6, and so on. So in this case, at this time in memory, page 6 was last referenced at time 1. Page 5 was last referenced at time 2. Page 2 was last referenced at time 3. And page 4 was last referenced at time 4, right? So if you have those timestamps, you can sort them, or you can just go through these and find the oldest one. So whichever one has the oldest timestamp would be the one you would select for replacement. That can be expensive. There's other ways you could do that for your own assignment. So you could just keep like a queue, and then every time you reference something, you put it to the front of the queue, and that way anything that was referenced the longest. So you'd have to use a queue where you can take things out of the middle of the queue and put them back onto the back of the queue, right? But that would work, and then that way, whenever you need to make a page replacement decision, the one that was on the end of that worked its way to the back of the queue, the end of the queue. Sorry, the one that worked its way to the front of the queue. If you're taking things off and putting them back into the back of the queue, the things on the back of the queue would be most recently referenced, and the things that work their way all the way to the front of the queue would be least recently referenced. So anyway, there's lots of ways you can implement a different LRU. Most people, just to give you a hint, do use something like a timestamp. So if you have to have an array that keeps your physical frames of memory that actually have the content, which pages on there are in each physical frame. But you could have a corresponding second array, which just keeps your timestamp, which is just which time each page was referenced. Okay, and then you could search through that to find the oldest timestamp. So anyway, there's a lot of overhead. So although LRU performs about as well as you can in terms of minimizing page faults, it can be expensive to implement. So it can take a lot of memory or big data structures to implement things like timestamps. So the clock policy is an attempt to compromise. So something, FIFO has like almost no overhead. All you need to do is keep a pointer, to keep a reference to the next frame that you need to replace. Whereas LRU can potentially have lots of overhead. You need timestamps for every frame and other information. Okay, so clock is an attempt at a compromise where you have low overhead kind of like FIFO, but it performs better. So it tries to take into account at least a little bit the likelihood that a page is going to be needed, and select pages that are less likely to be needed for replacement. Okay, so to implement a clock policy, and you don't have to do clock policy for the programming assignment, but you might need to do some clock policies for your test or for the written assignment, for example. So for one thing, for the clock policy, we're going to we are gonna keep a little bit of overhead, but we're just gonna use one bit of information. So every physical frame is gonna have one bit. Well, actually, we need probably 2 bits at least, but one bit that we'll talk about here, the use bit. Okay. So the use bit, and I'll call it U. Just keeps track of whether a frame has been recently referenced or not. Okay. Initially, when a page is loaded, so when a page is initially loaded, when loaded, the use bit we will initially set it to 1. Okay, and then likewise, every time also when a page is referenced, so when referenced, if the use bit is 0, we will reset the use bit to 1. Okay, so that, again, the use bit is meant to keep track of. It's not a full timestamp, but pages that have been more recently referenced or more recently loaded are more likely to have the use bit set to 1. And so how does the use bit get set back to 0? Well, that's where the actual clock page replacement algorithm comes into play. So for the clock algorithm, so the first thing we do is we keep a pointer, just like Fifo. So we keep a pointer to the next frame that we're going to be considering as a candidate for replacement. So starting at our frame pointer, so starting at the frame pointer, if the use bit is equal to 0, we found the page that we're going to select for replacement. So as soon as we find a use bit in a frame where it's 0, we select that page for replacement. And then if we select a page for replacement, we put the frame, we point the frame pointer to the next frame after the one that we replace. So frame pointer goes to the next frame. Frame pointer next. All right. But if the use bit is 1, if it's 1, instead we're not going to select that page for replacement. So instead we will set use bit to 0. So that's how use bits get flipped from 1 to 0. We set it to 0, and then we move the frame pointer to the next frame, and go back to the next step. So then we consider the next physical frame of memory. Okay, do that again. All right. So that's the basics of a basic clock algorithm. Okay, and most real operating systems use some version of the clock algorithm because it's a good compromise between first in, first out, which has bad performance in terms of having too many page faults. It's a compromise between that and LRU. So the only overhead here is an additional bit for every frame that we need to keep track of, this use bit. But otherwise, we're using a frame pointer and we're treating our buffer our frames as a circular buffer, kind of like we did for Fifo. But we don't just select the next page in a first in, first out manner. We do take into consideration some information about whether a page has been used recently or not. And we skip over pages that seem to be having been referenced more recently, and don't replace them. Okay. So let's just real quickly show an example of page replacement. So I'll just skip right to where we start. So initially, again, our first 4 references aren't replacements, but page placement decisions. We load memory. So initially, when we start with memory, all these pages have been referenced, and we've never had to make a page replacement decision. So our frame pointer is pointing to the first frame, and our book uses like a little star to represent when the use bit is set to 1. So all of these pages, when they were loaded, when they're replacing the memory, like we said here, are going to start out with their use bit being set to 1. All right, so they all have little stars. So then we do like we did normally. So we have a hit. So nothing happens on a hit. Memory stays the same. The page point, the frame pointer stays the same at the same location, and the use bits are not modified. All right. We have another hit. So again, everything is going to stay the same, so we still have the content 6524. All use bits are set, and we're still pointing frame 1. And now we finally have our first fault, so we have to make our first page replacement decision, okay? So notice here, I mean, all the use bits are 1. So what happens when all the use bits are 1 is the frame pointer ends up scanning all the way through memory, flipping all the use bits from 1 to 0, and it ends up back where it starts. And that will be the first page that it will finally find where the use bit is 0. So what happens is we scan through memory, all the use bits get set to 0, we end up back at frame 1, and we select page 6 then to be kicked out and replaced with page 3, okay? But so when 3 gets loaded into memory, its use bit gets set to 1. All the other pages are still where they were in memory, so we have page 5, 2, and 4, but their use bits are 0 now, so I don't put the star there to indicate their use bits are unset. They're all 0. And our frame pointer, since we've replaced our page into frame 1, our frame pointer is now pointing to frame 2 here, okay? So the next time we need to make a replacement decision, we're going to start scanning from frame 2. So now we have a reference to 5, that's a page hit. So now something does happen on a page hit for the clock policy, and I probably should have mentioned that something does happen on a page hit for LRU as well. So you have to update your timestamp, and in the clock policy you have to update the use bit. So in this case, we had a reference to page 5, so we should set the use bit back to 1 for page 5. So its use bit gets set to 1. 3's use bit is still 1, and 2 and 4's use bit are still 0, and our frame pointer is still pointing to page 2. But now, since 5's was referenced recently, its use bit is 1, so when we start scanning from there, it's not going to be selected for replacement. Its use bit first has to be flipped back to 0, and the buffer has to go back around one more time before we would consider page 5 again for replacement. Okay? So again, we have another hit for page 3. Page 3's use bit would get set to 1. It's already set to 1, so nothing really happens this time. So 3 has use bit set to 1. 5's use bit is set, and then 2 and 4's use bit are 0. And our frame pointer here is still at frame 2. Now we have a page fault, and this will be our first example where we're going to scan through and not scan all the way through memory. But we're not going to replace page 5, we're just going to flip its use bit from 1 to 0. So 5's use bit becomes 0. But when we scan down now, we find that frame 3, the use bit is 0, so we're going to select page 2 for replacement by page 6. It comes in with the use bit set to 1, okay? And our frame pointer now points to the page after we just to the frame after where we just replaced, so it's now pointing to frame 4. And then the other content stays the same. So frame 4 still has page 4 in it, and frame 1 still has page 3 in it with the use bit set. All right. And to continue on, so now we're going to have another page fault. So 7 causes a page fault. Our frame pointer is pointing to frame 4, whose use bit is set to 0, so we're just going to kick out 4 and replace it with 7, whose use bit will come in with 1. Our frame pointer will wrap back around and go back to frame 1, and the rest of the contents of memory will stay the same. So 3 with the use bit set, 5 with it unset, and 6 with it set. And then we have a reference to page 5. Our frame pointer is pointing to frame 1. The use bit is 1, so we're going to unset it, but skip over, not replace frame 1. And then we'll land on frame 2's page 5 has a use bit of 0, so we'll kick out page 5. Oh, I'm sorry. I made a mistake there. Forget what I was just saying. Page 5 is actually a hit, so nothing happens. Sorry about that. Well, something does happen, so 5's use bit gets set to 1. Otherwise, everybody else stays the same. So 3 still stays the same with the use bit of 1. 6 has a use bit of 1. And 7 has a use bit of 1. Okay? So we end up with the contents 3, 5, 6, 7. We end up with our frame pointer pointing to frame 1. And we end up with all of our items having the use bit set. Okay? So that's just an example of of our 4 basic page replacement algorithms. So let me go back real quickly to our programming assignment. So, like I said, you need to implement LRU and Fifo. So from the command line, I'm going to select either LRU or Fifo by using the first command line parameter. And then the second command line parameter is the number of physical frames you're supposed to simulate in your page replacement memory management simulation, okay? So in the example I just worked out on this video, we were using 4 physical frames of memory. But I can specify this on the command line. So you need to implement your system so it can work with whatever number of physical frames. And again, I think I say somewhere in here that you can assume that I won't give you a simulation ever with more than 10 physical frames. So if you want to, you can use statically created arrays of size 10 to represent your physical memory and maybe to hold things like your timestamps and stuff like that. Okay. So the input files represent a page stream. So here, instead of going from left to right, it goes from top to bottom. So each line contains a page reference. This reference is actually the same set of page references used in the example in our textbook. So you can see that the correct answers for this, our textbook was also using 3 physical frames of memory. So you can compare your implementation of Fifo and LRU to this. If you want to, you could also create a second page stream simulation using the page stream I just showed you in this video. If you want to compare, have a second set of page stream references to debug your programs with. All right, and then for the output, you basically have to, for every time step, you have to show which page was referenced at that time step, and you should show the contents of memory after you do your page replacement or page placement, okay? So at time 0, there was a reference to page 2, so we ended up placing page 2 into frame 1, okay? And then, at time 1, there's a reference to 3, time 2, there's a reference to 2. That was a page hit. So notice in this particular page stream from our textbook, even during the initial placement of pages, you can have page hits as well. So you do have to be checking whether it's a hit or a miss. You shouldn't be putting page 2 back into frame 3 and having 2 copies of it. There should always only be 1 copy of the page in memory. Okay. So just some hints. I mean, LRU, least recently used, shouldn't be all that difficult to implement. You just have to keep 1 pointer, or actually just 1 integer value, which keeps track of the next frame that you're going to place or replace a page in if you need to. The only difficulty you need to do is you do need to first check whether it's a hit or a miss, okay? But the same code, the same algorithm you use to check whether it's a hit or a miss is always going to be the same whether you're using a Fifo or an LRU or a clock. Okay, so my example solution, I implement the check whether it's a hit or not as a function. Okay, so I give the current physical frames of memory and the current page reference, and it returns true if it's a page hit, or false if it's a page miss, just as an example, right? So yeah, you'll have to implement something that can determine some code that can determine whether it's a hit or a miss, and then finally, as I already gave some hints about, for the more difficult algorithm is the least recently used, the LRU. So do the Fifo first. Most people, even if you've been struggling on past programming assignments, should be able to actually get the Fifo. I mean, as long as you can do C and know how to program with arrays in C. Doing Fifo, first in, first out, is not particularly difficult. LRU, my suggestion is, do use a timestamp. That's the most straightforward way to do it. So have both an array that represents your physical the pages in your physical frames of memory, and an array that represents the timestamp of the last reference to each page. And then you would just have to implement something that searches through that and figures out, which one has the oldest timestamp. Okay. All right, so that's it. So hopefully that will be helpful, give you some good information to start on understanding the page replacement software policy decisions for operating systems, and in particular your programming assignment on page replacement memory management schemes. All right, good luck.